After decades of research, construction, and a Christmas Day launch, we are getting more full-color images from the James Webb Space Telescope.
The most distant human-made object in the universe is sending usable information to Earth again.
For years, Neptune, our solar system's icy blue sentinel on the outer edge, has maintained a quiet mystery. Shielded by its great distance from the sun and cloaked in layers of turbulent atmosphere, Neptune has often been seen as one of the less dynamic planets in the solar system. That all changed when the James Webb Space Telescope captured something truly extraordinary: a massive celestial object colliding with Neptune's atmosphere. This wasn't a minor meteor shower or an icy fragment grazing the edge of its orbit. It was something far more significant, and its implications are nothing short of profound. Before we start, smash the like and subscribe buttons for more updates. The initial images arrived in flashes, data packets sent back from the James Webb Telescope as it gazed deep into the darkness of space. At first, it appeared to be a subtle distortion in Neptune's upper cloud layers, something transient or perhaps even an imaging artifact. But then, as analysts dug deeper, the evidence piled up rapidly. A sudden flare of heat signature, a gravitational wobble, and swirling patterns in Neptune's atmosphere all suggested a singular event of staggering proportions. A colossal object, most likely a rogue planetoid or perhaps even a fragment of a distant Kuiper Belt body, had slammed into Neptune's atmosphere, igniting a chain reaction of turbulence, energy, and shockwaves. The object in question was not a comet or asteroid of the sort typically associated with planetary impacts. Its trajectory, analyzed in reverse, suggested an origin beyond the orbit of Pluto, likely from the distant and still poorly understood Oort Cloud. Moving at a staggering velocity, this icy behemoth, potentially dozens of kilometers across, entered Neptune's gravitational well and made direct contact with the upper atmospheric layers. Unlike terrestrial impacts where craters or surface scars are left behind, Neptune's gaseous envelope absorbed the force, converting it into colossal thermal waves and violent storms that rapidly spread across the planet's visible surface. James Webb's infrared capabilities played a critical role in capturing the immediate aftermath of the collision. Within hours, a massive hotspot emerged in the upper atmosphere of Neptune, one that radiated significantly more heat than the surrounding clouds. Typically, Neptune's cold environment hovers around -200 degrees Celsius, but the impacted region spiked by over 30 degrees. The visual disturbance was equally mesmerizing. Jet streams that had remained consistent for decades suddenly shifted course, and new vortices began to swirl around the impact zone like galactic hurricanes unfolding in slow motion. The collision revealed something even more startling than the event itself. Layers of Neptune's atmosphere previously shrouded from view became temporarily exposed. The sudden heat pulse stripped back portions of the methane-rich haze, allowing astronomers to glimpse deeper into Neptune's composition than ever before. It was like peering through a keyhole into a chamber that had never been opened. Chemical signatures, thermal dynamics, and structural data all flooded into the James Webb sensors, giving humanity an unprecedented opportunity to study a gas giant in real time under extreme duress. More than just a rare spectacle, the collision carried massive scientific implications. One of the most immediate was related to planetary defense and the dynamics of space objects in the outer solar system. If an object of such scale could find its way into Neptune's orbit and survive long enough to create a collision, it raised urgent questions about what else might be lurking in the cold expanses beyond Neptune. These rogue celestial bodies, often undetectable until they move closer to the inner solar system, pose a threat not just to distant planets, but potentially to Earth itself. The collision served as a blunt reminder that the solar system is far from a stable, predictable neighborhood. Another area that experienced a rapid acceleration due to the impact was the study of gas giant atmospheres. Previously, most of what was understood about Neptune came from the limited data collected by Voyager 2 in the 1980s and subsequent telescope observations. The Webb telescope's high-resolution imaging, particularly in infrared and ultraviolet wavelengths, provided live data as Neptune's atmospheric chemistry reacted to the impact. New compounds were detected, ones that may have been released from the icy body itself or forged in the furnace of the collision. These chemical trails painted a vivid picture of atmospheric mixing and turbulence, offering a blueprint for understanding similar processes on other gas giants like Uranus, Saturn, and even exoplanets far beyond our solar system. There was also a gravitational ripple effect. Though Neptune is immense, 17 times the mass of Earth, the impact was so substantial that a detectable disturbance echoed through its magnetosphere. The James Webb Telescope observed fluctuations in Neptune's magnetic field, which hinted at internal shifts beneath the atmospheric layers. It was as though the collision had sent vibrations into the planet's core, causing subtle shifts in how it interacts with solar wind and cosmic radiation. These readings may become the basis for a whole new field of study: planetary seismology for gas giants, interpreting the internal reactions of planets with no solid surface in response to external forces. Notably, this was the first time in history that humanity has observed such an event with the level of clarity provided by the James Webb Telescope. The depth and range of its instruments enabled scientists to record the collision in multiple spectra, each revealing a different dimension of the phenomenon. From the visible light that captured the swirling high-altitude clouds, to the infrared maps that traced the heat wave across Neptune's face, every wavelength offered new insight. It was like watching a cosmic autopsy unfold in real time. This data overflow became a treasure trove for planetary scientists, astrophysicists, and chemists alike. Research institutions around the globe began analyzing terabytes of information, working to model the event and understand its cascading effects. Simulations recreated the moment of impact, measuring the energy release, atmospheric response, and thermal diffusion. Every variable added clarity to one of the most mysterious planets in our system. Questions that had lingered for decades about Neptune's inner composition, its heat source, and its dynamic weather systems were now closer to being answered. Even the planet's famous storms, the Great Dark Spots, were influenced by the event. These massive storm systems, similar in some ways to Jupiter's Great Red Spot, are known to appear and disappear without warning. After the impact, new storm patterns emerged, swirling with unusual symmetry and force. It was as if the kinetic energy from the collision had jump-started Neptune's atmosphere into a new rhythm. The equatorial jet streams accelerated, latitudinal wind belts shifted, cloud formations rose and fell in strange choreography, creating mesmerizing ripple effects, captured in exquisite detail by the Webb telescope. Astronomers noted something especially curious. The impact seemed to cause an alignment in Neptune's ring system, which had previously been seen as faint and fragmented. For a brief window of time after the collision, Webb's sensors detected increased brightness in several of Neptune's narrow rings. The cause is still under study, but one theory suggests that shock waves from the impact disturbed nearby particles, causing temporary compression and increased reflectivity. This could also suggest that Neptune's ring system is more dynamic than once thought, with a sensitivity to both internal and external forces. Beyond Neptune itself, the collision had ramifications for our understanding of the solar system's formation and ongoing evolution. It challenged the assumption that the outer planets exist in a kind of frozen stability. Instead, it painted a picture of an active, dynamic outer solar system, where collisions, gravitational disturbances, and unexpected interactions still unfold. The scale and rarity of such an impact demonstrate that the outer planets are not immune to the chaos of cosmic forces. The broader implications stretched even farther. If such a body could be pulled into Neptune's orbit and collide with such force, it could hint at gravitational dynamics we don't fully understand. The role of the Kuiper Belt and Oort Cloud in shaping planetary interactions may be more significant than previously believed. Neptune, often considered the solar system's outer gatekeeper, might be experiencing more inbound material than assumed, acting as both a shield and a target for errant celestial wanderers. The event also sparked renewed interest in planetary weather modeling. For years, simulations of Neptune's climate were based on limited data and carried wide margins of error. With the influx of real-time observational data during and after the impact, scientists began refining models to incorporate extreme events. These new simulations included variables like heat pulse injections, gravitational shifts, and the formation of transient storm cells, offering a more dynamic, accurate portrayal of how Neptune lives and breathes beneath its cloud cover. More intriguing still, there were signs that the impact had temporarily altered the luminosity of Neptune as seen from a distance. Webb sensors detected a fluctuation in the planet's reflected light, which briefly increased before stabilizing again. If this change had occurred in an exoplanet light years away, it might have been interpreted as a natural variability or even a sign of artificial interference. Observing it so close to home helps refine the methods astronomers use to study distant worlds, improving the accuracy of exoplanet analyses in future research. A moment of pure scientific drama also unfolded as Neptune's moons reacted to the collision. Triton, Neptune's largest and most intriguing satellite, exhibited subtle shifts in its own orbital behavior. Already considered a captured Kuiper Belt object, Triton may have resonated with the gravitational echoes of the impact. Observations noted tiny changes in its surface activity, possibly triggered by tidal interactions or by particle dispersions from Neptune's disturbed magnetosphere. Even Nereid and Proteus, two of Neptune's lesser-known moons, showed altered albedo readings, suggesting that the energy released might have reverberated further than expected. The event was not just a triumph of observation, but a reminder of the power of foresight. The James Webb Telescope had been placed in position precisely to uncover hidden mysteries like this. Its ability to see farther, clearer, and in more wavelengths than any telescope before it finally paying off in full. The collision on Neptune marked one of its most monumental early contributions to space science, proving its capability not just as an observer of distant galaxies and exoplanets, but as a vigilant sentinel within our own cosmic backyard. With Neptune now temporarily transformed by the impact, its vibrant atmosphere pulsing with new energy and motion, scientists watch closely, knowing this event will yield insights for years to come. The impact stands as a testament to the dynamic and ever-changing nature of our solar system, where even the farthest reaches are subject to drama, transformation, and revelation. What was once a quiet, distant world has become a focal point of planetary science, ignited, quite literally, by a collision of titanic proportions. The unfolding consequences of the monumental collision on Neptune extend far beyond the immediate drama captured by the James Webb Space Telescope. Though the initial impact was an explosive and visually spectacular moment in astronomical observation, the real significance lies in the slow-burning revelations that continue to emerge. The universe, indifferent yet immensely complex, has offered scientists a unique window into deep planetary mechanics and cosmic interaction, one that promises to reshape our assumptions about planetary behavior, orbital architecture, and interplanetary migration. One of the most critical domains of research sparked by the collision is the study of kinetic energy transference in a gaseous environment. Unlike terrestrial impacts, where a celestial body meets a solid surface and causes direct disruption, like the Chicxulub impactor that helped bring an end to the age of dinosaurs, impacts on gas giants behave differently. In Neptune's case, the massive object's energy was dispersed through varying atmospheric densities, generating an entirely different form of planetary stress. Shock waves radiated vertically and horizontally through the planet's fluid-like atmosphere, creating towering atmospheric ripples that were tracked by the James Webb spectrometers. These vertical atmospheric ripples aren't just aesthetic anomalies. They represent fundamental changes in the planet's internal convection and temperature distribution. Neptune, long known to emit more heat than it receives from the sun, has always perplexed scientists with its mysterious internal heat source. The energy from the impact temporarily supercharged these internal systems, allowing scientists to isolate the layers responsible for heat retention and radiation. Observations showed that deep convection currents were thrown into disarray, ascending faster and hotter than previously seen, revealing a layered atmospheric system more dynamic than any model had predicted. Equally groundbreaking was the identification of high-altitude ice crystal plumes forming in the stratosphere. These crystals, resulting from rapid cooling after the initial thermal bloom, resembled phenomena seen in Titan's atmosphere more than those typically associated with Neptune. Their chemical makeup suggested the presence of exotic volatiles, substances like ethane, diacetylene, and potentially even traces of hydrogen cyanide, brought to the surface or synthesized during the extreme energy reactions. These elements, frozen into microscopic particles, reflected sunlight in ways that created iridescent halos over the impact zone, beautiful, fleeting, and scientifically invaluable. The pressure differential created by the impact had a significant influence on Neptune's upper troposphere, leading to jet reconfiguration on a global scale. Scientists monitoring zonal winds were astonished to find that the speeds of these winds increased by up to 30%, particularly around mid-latitude bands. Such acceleration persisted well beyond the immediate aftermath, suggesting that Neptune's weather systems had entered a new state of equilibrium, one that could potentially last for decades. It also brought into question the long-held idea that the gas giant's atmospheric dynamics were primarily influenced by solar radiation and internal convection. Now, external impacts must be considered significant enough to cause permanent shifts in planetary weather architecture. While the main spectacle was Neptune itself, equally important was the influence this event had on the study of interplanetary orbital mechanics. The object's trajectory and speed, reconstructed with data from both Webb and supplementary telescopes like Hubble and ALMA, painted a picture of a body disturbed from a long stable orbit, likely from the distant ghostly boundaries of the Oort Cloud. This ejected mass did not follow the clean, predictable lines of gravitational shepherding. Instead, it took an erratic inclined path, suggesting it had been influenced by multiple gravitational wells before finally succumbing to Neptune's immense pull. This path, when overlaid with known locations of trans-Neptunian objects TNOs, revealed surprising correlations. It appears that the outer solar system may contain more loosely bound or completely unbound bodies than previously believed, essentially a fleet of rogue debris drifting through deep space. The Neptune impact wasn't just a chance event, it was a signal flare indicating an entire realm of orbital instability that we've only begun to understand. These findings have initiated renewed investment in tracking near-Neptune objects, with dozens of sky surveys recalibrated to focus on these dim, slow-moving threats. Additionally, the impact triggered discussions about the theoretical existence of Planet 9, the hypothesized massive object far beyond Neptune that could explain gravitational anomalies in TNO orbits. The perturbation that brought the impactor into Neptune's domain may have been influenced by such a body. While this remains speculative, the increased attention on distant solar system dynamics has breathed new life into efforts to detect such hidden giants. The collision offered more than physical disturbance. It brought philosophical and scientific momentum, pushing us toward answers to questions that have lingered for decades. On a different front, the collision allowed scientists to re-examine Neptune's radiation belts. Unlike Earth or Jupiter, Neptune's magnetosphere has always appeared somewhat irregular, tilted, and offset in puzzling ways. After the impact, instruments detected a spike in charged particles. Plasma density increased significantly in the region where the collision occurred. This radiation burst gave insight into how impacts can momentarily alter magnetic field topology, perhaps even enabling subspace charge leaks into surrounding regions. Such conditions could influence future missions to Neptune, forcing engineers to account for temporally variable radiation zones, especially for any orbiters or atmospheric probes. The James Webb Space Telescope also detected trace amounts of ionized oxygen and nitrogen in Neptune's upper layers, likely remnants from the vaporized impactor. These atomic traces carried unique spectral fingerprints that didn't match any known pattern of solar interaction. The implication is profound. We now have access to the elemental profile of a celestial body from the outer solar system, one that was effectively incinerated in Neptune's upper atmosphere and scattered across its skies. These elements were processed under conditions of heat and pressure unmatched in controlled laboratories, providing a dataset valuable for comparative planetary chemistry and even stellar nucleosynthesis modeling. Another area now under intense study is the potential for ripple effects through Neptune's gravitational sphere of influence. The gas giant exerts tidal forces on its moons and nearby Kuiper Belt objects. A shift in mass distribution, even one as transient as this impact, could cause measurable changes in moon orbits or rotational stability. Early telemetry suggested Triton exhibited a micro-precession, a wobble in its axis of rotation. While subtle, this deviation could influence long-term tidal heating and internal activity, perhaps leading to cryovolcanic behavior or tectonic shifts within the moon. It would be the first documented case of an external planetary impact indirectly triggering geological activity on a moon. This event also unlocked new potential for understanding high-altitude lightning formation. During the moments following the collision, a series of high-intensity, low-duration light flashes were observed in the upper atmosphere, brighter and more frequent than typical storm activity. These were not mere electromagnetic pulses, but full-scale lightning discharges, likely catalyzed by the sudden vertical motion of hot gases and volatiles. These discharges created ozone pockets and unique NOx compounds, providing a laboratory for studying how planetary-scale electrical storms form under extreme duress. This has implications not only for Neptune, but for gas giants across the universe, many of which show lightning activity in exoplanetary studies. One of the more exotic consequences involved Neptune's tenuous ring arcs, sections of its ring system that appear incomplete or unevenly distributed. The collision seems to have created a standing wave through these arcs, causing temporary reinforcement in areas previously considered gravitationally unstable. This raises fascinating possibilities about how ring systems evolve. Traditional understanding assumes static processes shaped by shepherd moons and long-term accretion. But the Neptune impact suggests ring structures can be actively manipulated by short-term energy events, leading to temporary stabilization or expansion before collapsing again. It's a dynamic dance, one that defies the slow-motion paradigm previously applied to ring formation. The burst of attention around Neptune has also drawn focus to its seasonal cycles, which span over 165 Earth years. Though changes happen slowly, the collision offers a rare stimulus, akin to throwing a stone into a still pond, that can reveal how deep layers respond over short and medium timescales. The event is now being modeled in tandem with Neptune's axial tilt and orbital position, offering a framework to understand how external events might trigger seasonal accelerations, atmospheric inversion, or even albedo feedback loops. These lessons could help refine our models for long-period exoplanets, especially those with eccentric orbits and slow rotations. Astrobiologists have taken a deep interest in the event, not because Neptune is a likely host for life, but because of what the impactor might have brought with it. Bodies from the Oort Cloud may have complex organic chemistry, preserved for billions of years in frozen darkness. The heat of the impact could have caused pyrolysis of these organics, releasing carbon chains, amines, or nitriles into Neptune's clouds. While this doesn't point to life, it expands our understanding of how organic matter is processed on gas giants, and how similar collisions could act as delivery mechanisms for prebiotic materials elsewhere in the cosmos. Jupiter and Saturn may have undergone similar events, but we've never observed one in such detail, until now. The societal and educational ripple effect of the Neptune collision is also worth noting. Public fascination with space surged in the days and weeks following the event. Visualizations from the Webb Telescope captivated millions, and educational institutions used the event as a springboard to teach about planetary science, orbital mechanics, and atmospheric chemistry. It was one of those rare moments where science broke through cultural noise, commanding global attention not through fear or speculation, but through raw, empirical wonder. This increase in visibility translated into renewed funding for space sciences and broadened support for future missions to the outer solar system. Amidst all this, perhaps the most understated but philosophically important realization was this: the solar system is still writing its story. For all our modeling and simulations, the cosmos continues to surprise us. The Neptune collision serves as a living chapter in a book we thought we understood. It's a reminder that planets aren't just frozen relics circling the sun. They are living dynamic entities capable of experiencing chaos, adaptation, and regeneration. We are fortunate to live in an age where we can witness such transformations in real time, with tools like the James Webb Space Telescope serving as our eyes in the dark. In the years to come, Neptune will likely continue to evolve in response to this event. The clouds will shift, the heat will dissipate, the energy will disperse into deeper layers, perhaps never to surface again. But the moment was caught, measured, and decoded. The data lives on, not just as numbers in a database, but as proof of how much we still have to learn and how much is yet to unfold. The impact may have passed, but its resonance, scientific, cultural, and cosmic, continues to echo through the void. In the ever-deepening ripple effects of Neptune's extraordinary collision, a new focus has emerged: time-resolved planetary monitoring. The James Webb Space Telescope's documentation of this cosmic event didn't stop at a few snapshots or spectral data sets. It provided continuous observational coverage over hours and days, enabling researchers to monitor the evolving aftermath as a dynamic process rather than a singular event. This revolutionized the methodology for outer planet research, proving the enormous value of temporal resolution when studying planetary-scale phenomena. Until now, most outer solar system observations relied heavily on brief, infrequent imaging intervals. This fragmented approach often led to data gaps, making it difficult to trace causality or system-wide changes after transient events like storms or potential impacts. With the Webb's sustained coverage of Neptune post-collision, scientists now have a complete time-lapse of planetary reaction on a molecular and atmospheric scale. This has unlocked the ability to track how gases mix vertically, how chemical signatures mutate in response to heat and pressure, and how photochemical reactions are initiated by energy surges. In particular, researchers are studying how certain trace molecules evolve over time after being injected into the upper layers. Photodissociation processes, which involve ultraviolet sunlight breaking molecular bonds, created unique compounds not normally observed on Neptune, including transient radicals and exotic ions. These compounds, unstable under normal conditions, persisted long enough for detection thanks to the rapid energy release and subsequent cooling cycle. Scientists are now investigating if such collisions can create short-lived atmospheric states that act as analogs to prebiotic chemistry, akin to what might occur on early Earth-like exoplanets under similar bombardment conditions. Another fascinating aspect involves the gravitational microenvironment around Neptune and how it was temporarily distorted by the impact. Though the gas giant's immense gravity remains dominant, a large impactor entering and distributing its mass through gaseous disintegration changed local gravitational gradients. These microshifts, detectable only through extremely sensitive Doppler readings and slight perturbations in orbital paths of nearby particles, have opened a new window into studying how mass redistribution, even in non-solid mediums, can create localized gravity pockets or gradients that influence particle behavior on short timescales. One unexpected consequence observed was a faint echo or resonance in Neptune's bow shock, the area where the planet's magnetosphere confronts the solar wind. Typically, this region remains relatively stable, shifting only slightly based on solar activity. However, days after the impact, Webb's instruments recorded subtle oscillations that propagated outward, resembling ripples on a magnetic pond. These shifts could be interpreted as magnetic reverberations caused by a sudden redistribution of charged particles within the planet's magnetosphere, essentially a magnetic quake, echoing the violence of the collision. This could help scientists develop new ways of measuring magnetic resilience and elasticity in other celestial bodies. Attention has also turned to the thermodynamic modeling of high-pressure shock events in hydrogen-helium atmospheres. Gas giants like Neptune are primarily composed of these light elements, but understanding how they behave under extreme and sudden pressure fluctuations is complex. The impact provided a real-world test case. Simulations built on the Webb data have begun to replicate the compression and expansion behavior of these gases under shockwave conditions. The results could significantly refine models used to simulate gas giants and brown dwarfs, substellar objects often difficult to study directly, but fundamental to understanding stellar formation and evolution. In the realm of exoplanetary science, this Neptune event has proven especially valuable. While we can't observe collisions on exoplanets with the same fidelity, the data from Neptune serves as a benchmark. Scientists can now calibrate their instruments to look for similar heat spikes, transient spectral lines, or atmospheric distortions in distant planets. These calibrations will improve our ability to detect and interpret extreme weather or impact events in alien worlds. In this way, Neptune's collision becomes a reference point for a universe full of unseen but possibly similar events. Further out, the long-term implications for Neptune's own orbital position are now being scrutinized. While it's unlikely that a single impact could significantly alter the path of such a massive planet, the principle of cumulative impacts is being revisited. If multiple such collisions have occurred over the solar system's lifespan, even minuscule nudges in gravitational vectors could add up. This might explain subtle deviations in Neptune's position from where it's predicted to be based on classical mechanics. Combined with influences from the hypothesized Planet 9 or the irregular mass distribution of the Kuiper Belt, this event has reignited interest in re-examining Neptune's long-term orbital evolution. Another subtle yet revolutionary insight involves atmospheric sound propagation. While Neptune lacks a surface for traditional seismic waves, the collision produced pressure waves that moved through the atmosphere like sound through water. Webb's instruments, while not microphones in the literal sense, detected density fluctuations indicative of acoustic waveforms traveling thousands of kilometers per hour through different strata. These sound waves, inaudible to human ears, carried information about temperature gradients, chemical distribution, and pressure levels, all of which are being modeled to reconstruct Neptune's layered atmospheric structure in 3 dimensions. For the first time, we are essentially listening to a planet breathe and react to trauma. This opens the door to a new planetary exploration technique, atmospheric acoustic tomography. By using disturbances like this impact as probes, we can use the resulting pressure waves to map internal atmospheric structures, potentially even identifying storm chambers, convection pathways, or upwelling heat zones. In the future, deliberately engineered probes might release controlled sonic booms to perform a similar analysis, an idea previously reserved for solid planets with known crusts and mantles. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Neptune's collision? We want to hear from you. Thank you for watching and see you next time.